Okay, so as we move into chapter 10, we move back a little bit into things that we were doing in chapters 7 and 8 with some hypothesis testing and things like that. It's not going to be exactly the same as those two chapters because our tests are going to look a little bit different. But one of the main tests that we do is called a goodness of fit test. So, some vocab throughout this. A multinomial experiment is a probability experiment consisting of a fixed number of independent trials in which there are more than two possible outcomes for each trial. The probability of each outcome is fixed, and each outcome is classified into different categories. And then to do a goodness of fit test, we use a chi-square test. So we're testing whether a frequency distribution is going to fit what it is expected to do. So it's going to say, this is what we think is going to happen. Is this really what happened? So we're going back to null and alternative hypothesis for the goodness of fit test. You generally are going to have a null hypothesis that's like the frequency distribution fits, and your alternative hypothesis is going to be that your frequency distribution does not fit. So it's not going to be like your typical mean less than or equal to 5 like it would have been in chapters 7 and 8, but it's going to be more of like an actual sentence. So when we find our test statistic, we're going to use observed frequencies and expected frequencies. So when we calculate expected frequencies, you have to assume that the null hypothesis is true, that it's going to fit that expected distribution. Observed frequencies are labeled with the letter O. So observed frequencies of a category is the frequency for the category observed in the sample data. So not what's expected, but what really happened. The expected frequencies are labeled with E. Okay, notice that it's a capital O and a capital E. Make sure you're using those. So your expected frequency of a category is the calculated frequency for the category. Expected frequencies are found by using the expected or hypothesized distribution and the sample size. So we're just doing a lot of multiplying. The expected frequency for the if category is E sub I equals N times P sub I. N is just your number of trials or the sample size. P sub I is the assumed probability of the if category. I don't want you to panic about that. It's nothing fancy. It's literally just, instead of saying like times our first category, times our second category, times our third category, that P sub I encompasses every category. So it's just whatever the probability is for the first category, the second category, the third category, and all of that. Okay, so in number 1, a tax preparation company randomly selects 500 adults and asks them how they prepare their taxes. The results are shown in the table. Find the observed and expected frequencies for each of the tax methods. So here's the good news. Your observed frequencies are super easy because your observed frequencies are literally whatever your survey results were. So our survey results when N was 500 are listed here: 98, 62, 220, 39, 81. That's O. That's your observed frequencies. So you don't have to find those because that's in the data that's given to you. When we find our expected frequencies, or E, we have to do a little bit more because we have to find how many should we have based on the sample size and the distribution. So we're just multiplying. Okay, so we had 500 adults selected. So we're going to multiply each probability or distribution by 500. So for the accountants, 500 times 0.24, 24% is a decimal, is going to give us 120. For doing it by hand, 500 times 20% is going to give us 100. Computer software, 500 times 35% is 175. Friends or family, 500 times 6% is 30. And then tax prep service, 500 times 15% is 75. So observed is always whatever your survey says. Expected frequency, you have to find yourself. So it's just your sample size, or whatever n is, times your distribution or probabilities. So your percentage of people that they're saying are using all of those things. Okay, so when we do a chi-square goodness of fit test, you have two conditions that you have to meet. The observed frequencies have to be obtained using a random sample, and each expected frequency must be greater than or equal to 5. Okay, those are both really easy to meet. Rarely are you going to have something that doesn't meet those conditions. And if you were to have one that wouldn't meet those conditions, it'd probably be number 2. It'd probably be that an expected frequency wasn't at least 5. So when those conditions are met, the sampling distribution for the test is approximated by a chi-square distribution with k minus 1 degrees of freedom, where k is the number of categories. So we're going back to degree of freedom. Instead of n minus 1 like it's always been, it's just k minus 1. K stands for categories. So to find your chi-square, it's the sum of your observed minus your expected, all squared, divided by your expected. Okay, basically we're just going to make a big table, so it'll be fine. Again, O is your observed frequency, E is your expected frequency. Okay, a chi-square goodness of fit test always going to be right-tailed. Okay, so we don't have to worry about two-tailed, left-tailed. It's always going to be right-tailed. When we perform a chi-square goodness of fit test, we're going to verify that the observed frequencies are from a random sample and every expected frequency is at least 5. We're going to identify the claim, state our hypotheses. We're going to make sure we know our level of significance, our degree of freedoms. We're going to find our critical value and rejection region. We're going to find the test statistic. We're going to reject or fail to reject, and we're going to interpret. Literally nothing has changed in the process since 7 and 8, chapter 7 and 8. So everything we're doing in the process is the same. The difference is coming in when we actually find our test statistic. Okay, so in number 2, a sociologist claims that the age distribution of the residents of a city is different from the distribution 10 years ago. You randomly select 400 residents and record the age of each. At alpha equals 0.05, perform a goodness of fit test whether the distribution has changed. So you guys are going to probably hate writing HO and HA now, but it is what it is. Because remember, HO is generally going to be that your age distribution stays the same and that your HA is that it's going to be different. However, you have to actually state what that distribution is in HO. So HO is going to be the age distribution in a town is expected to be 16% at 0 to 9, 20% at 10 to 19, 8% for 20 to 29, 14% 30 to 39, 15% 40 to 49, 12% 50 to 59, 10% 60 to 69, and 5% for 70 plus. The good news is HA is just that the age distribution differs from the expected. Which is our claim in this case, because we want to tell whether the distribution has changed. So if it's changed, it's going to be different. So when we find our critical values and all of that, we've got alphas at 0.05. We're using a chi-square table, which in the back of your book, because you probably don't have yours still from class, but your chi-square table is on page A19 in the back of your book. So we're going to our alpha value of 0.05, and then our degree of freedom is k minus 1. So k is the number of categories. So in this case, age groups. So we got 1, 2, 3, 4, 5, 6, 7, 8 age groups or categories. So our degree of freedom is going to be 7. So we're going to go to 0.05 and down to 7, which gives us 14.067 for our critical value, which means our rejection region is going to be greater, because it's always right-tailed, than that 14.067. So now it's just a matter of finding our test statistic. So remember I told you we were just making a table. So survey results are your expected, or your observed. So we need to find our expected values, and then we're going to subtract our observed and our expected, and then we're going to square our observed and our expected, and then we take that observed minus expected squared and we divide it by what is expected. So remember, to find your expected, you're taking the n value, your sample size, which is 400, and multiplying it by the distribution, or by the percentages as a decimal. So 400 is our population, so 400 times 16%, or 0.16, is 64. 400 times 20% is 80, times 8% is 32, 14% is 56, 15% is 60, 12% is 48, 10% is 40, 5% gives us 20. So now we're subtracting our observed and our expected. So 76 minus 64 is 12, 84 minus 80, 30 minus 32 is negative 2, and we've got 4, negative 6, negative 8, 2, and negative 6. So now we're going to take our observed minus our expected, and we're going to square each of those numbers. So 12 squared, 4 squared, negative 2 squared. Remember, when you square a negative, it's always a positive. 4 squared, negative 6 squared, negative 8 squared, 4 squared, and negative 6 squared. And then we have to take each of those values and divide it by what it was expected to be. So 144 divided by 64 is going to be 2.25. 16 divided by 80 is 0.2. 4 divided by 32 is 0.125. 16 divided by 56. Now, we've had decimals that end so far. If you don't, at least go to 3 decimals. You can go to more, but at least go to 3. 36 divided by 60. 64 divided by 48. 4 divided by 40. And 36 divided by 20. So to find our test statistic, we just need the sum of that last column. So we're just going to add all of those up. So 2.25 plus 0.2, 0.125, 0.286, 0.60, 1.333, 0.1, 1.8, which gives us 6.694. So that test statistic is 6.694, which is not greater than our rejection region. So 6.694 is not greater than 14.067. So we fail to reject HO, which means we don't have enough evidence to support the claim that age distribution differs from that of 10 years ago. Okay, so I know that was a lot of writing, especially for your HO and HA, but the way you interpret is exactly the same as it would have been before. If it fits into that rejection region, if it makes it true, you reject it. If it doesn't make it true, you fail to reject it. Okay, so number 3, researchers claimed that the number of different colored M&Ms in a bag of peanut M&Ms is uniformly distributed. To test this claim, you randomly select a bag that has 180 M&Ms, so that's going to be our sample size. The results are in the table. Use alpha equals 0.05 to test the claim. So, key word here is that they're uniformly distributed, which means the percentage of every single color should be the same. So, if we have 180 M&Ms and we have 6 different colors, the good news is it makes finding your expected much easier because they're all going to be the same. We don't have to worry about a percentage and multiplying that percentage by n, because if they're uniform, we have to have the same number. And that number is going to be 30. So now we can do our observed minus our expected. And then square those. And then divide those by the expected. So we're dividing all of those by 30. So we get 2.133.3, 2.133, 4.033, 4.033, and 0.3. So remember, I just took this column here and divided it by our expected, or 30, to get all of those values in the last column. So if I add those together, I should get 12.932. So I did all the work before I did any of the writing, just because it was easier in my mind. It doesn't really matter as long as you have it. H, O, and HA are easier in this one because since we know it has to be uniform, we can just say that for HO. And they're saying that it is uniformly distributed, which would make HO our claim. We had 6 colors, so our degree of freedom is going to be 6 minus 1, or 5. So when we look up our critical value, we're going to 0.05 on the table down to 5, which is going to give us 11.071. Right-tailed means it's always going to be greater than that. So this number that we found right here is our chi-square value. So we're just comparing that. So 12.931 is greater than 11.071. So since it's greater than 11.071, we reject HO. So we have enough evidence to reject the claim that the color distribution in a bag of M&Ms is uniform. Hopefully, even though it's been a while since we've done some hypothesis testing, that makes sense to you. If not, get on Google Meet, or if it's after class but before 3, you can request a Google Meet with me. Shoot me an email, text me, whatever. But if you get stuck, let me know. Your homework will be posted on the assignment, but it's just page 532, 2 through 16 even. So it shouldn't take you too long. Make sure you show your work, because if you don't show your work, I'm not going to give you the credit. So don't forget to show your work when you send me your homework.